Is it? Well, okay. So let me start anyway. I'm going to share. I'm going to record on this thing. I hope you can see my screen. Say yes or no. Someone?
Yes, sir.
Okay. Okay.
Yes,
Yeah.
sir.
Yes. Any questions? Did someone say something? Oh, okay. Yeah. So what is the SAT decision problem? Okay. Just to recollect your memory. So given an arbitrary quantifier-free formula phi, okay, for propositional logic, whether you have quantifier or not doesn't matter because the quantifiers can be eliminated through enumeration, like we've seen. Check any of the following. Okay. Satisfiability, and produce a satisfying, check if there is a satisfying assignment. If so, produce it. Unsatisfiability, check if there's no assignment to the variables that can satisfy the formula. Or validity, okay, holds for all modules. The important thing is that, so you can have any formula, the propositional formula can contain any Boolean proposition, okay, any Boolean function in it, okay. So that is what, given any formula using any kind of Boolean connectives representing, the idea is to come up with an automatic procedure to decide any one of these satisfiability problems. Okay. Please, since it is an online class for the first time in this course, I would like for you to raise your hands or turn on your turn off mute to ask any questions that they need. The prepositional SAT checking is NP complete, okay? Because you can, it's actually a classical NP complete problem. And almost all, lots of other problems are shown to be NP hard and NP complete, but reducing them to Boolean satisfiability. Now, when we talk about decision procedures, it's important to kind of recap normal forms for prepositional formulas. What is a normal form? A normal form defines a set of syntactic constraints on the syntax of the formula, such that every Boolean function is representable in the normal form. A normal form defines a set of syntactic constraints in the way that you can construct your formula. So just to quickly run through, conjunctive normal form is a product of Max terms. It's a conjunction of clauses we've already seen, where a clause is a sum of literals, like in this example shown. A DNF, a disjunctive normal form, is a conjunction of, oh, this is a mistake. It's a disjunction of cubes, okay, where a cube is a product of literals, and we call them in terms like this. There can be other kinds of normal forms as well. Okay? One such thing is, this is a class of normal forms called negation normal form. negation normal form is if it's a formula where the negation occurs only at the leaves of the formula. Okay, for example, this formula is not in negation, it's not in negation normal form. CNF and DNF, by definition, they are negation normal forms. The reason I'm just recapping this is because these decision procedures, various decision procedures that exist for Boolean satisfiability, for checking Boolean satisfiability, leverage the structure of these formulas. They all rely on the formulas being expressed in a particular normal form. Okay. Now, negation normal form is a nice normal form because it satisfies this monotonicity property. Okay. If a formula is in negation normal form, and if phi is, phi is a formula and alpha is some satisfying assignment for phi, and let's suppose that pos alpha of phi is the set of literals in phi satisfied by alpha. Okay, I mean those literals in the assignment alpha that make in the assignment alpha, this gives the set of literals that make those literals to become true. So if it is a negation normal form, it satisfies this property for every other assignment to the literal, such that, that makes more literals in the formula go to true. That's what this says. Okay, pos alpha of phi is a subset of pos alpha of prime. So prime, then alpha prime also satisfies phi. Okay, as long as you make more literals become true, and you can see why that is the case. Okay, because if there is a literal that is already making something to be true, if it's then by making more of them, you can always retain its satisfiability. So this is just an example of how when you have formulas in a certain normal forms, there are certain properties that they satisfy which can be exploited. Okay. Now, there is another normal form, which I guess most of you have heard CNF, DNF, okay? But there is another one which is also very widely used to decide Boolean satisfiability, and that is, in parlance, it is called binary decision diagrams. Maybe some of you have already seen it in your logic thing. It's what I call as an if-then-else unique normal form. I say unique normal form because CNF and DNF, they are normal forms in the sense any Boolean function can be represented by a formula in that form, but these are not unique. Okay, you can have different CNFs representing the same function, whereas here you can use BDDs to represent. Okay. Excuse me. To give an example, consider here is this formula, BDD normal form. The formula is constructed using only, okay. By the way, I mean, you have to unmute and then, sound out, if you have any questions, because I don't see your arms, your hands raising since I have minimized your interaction. Okay, window. In this BDD normal form, a formula is constructed using only one of the following functions. Okay, the constant true, 1, the false, 0. And you can have the formula in this if-then-else form, where there is X. This is an if-then-else expression, conditional expression, where in the condition you can only have a variable, that is a variable, that X is true, and the if and the then and the else part are terms which are themselves in this BDD normal form. And the meaning is if X is true, that variable has a truth assignment of true, then the truth of this entire formula is T1, whatever T1 is, and else T2, where T1 and T2, like I've said here, like I said before, are BDD norm form that don't have X. Okay, X can, each variable can only appear in once in each of the nested term. Okay. So, for example, X or Y can be represented by this nested if then else expression. Okay. So if X is true, of course, this OR is true, correct? The disjunction, therefore it becomes 1. If not, then the truth value of this disjunction of X and Y depends on Y. If Y is true, then it is 1. Otherwise, it is false. That's the case where both X and Y are false, and therefore it is 0. So negation, for example, can be expressed as in this way. If X is true, then it has to be 0, else it has to be 1. Okay. So a BDD representation of a Boolean function is, like I said before, is canonical. That is, it is unique. If the ordering of the variable, see, this kind of a thing is, you can view this as a tree structure, because a nested if then else can be viewed, can be represented like a tree where the leaves have ones and zeros, and the non-terminals in the tree have variables in the that appear in this if then else. Okay, as long as you query the variables on every path, okay, in the same order, if you preserve that, then has a unique normal form. Okay, and that makes this BDDs very efficient in order to check. Okay, now once you construct the BDD for any Boolean formula, checking whether it is satisfiable or not is very efficient. It's actually polynomial. Okay, all you have to check is if there is a path. Okay, as long as there is a path that leads to a 1, it is satisfiable. Unsatisfiability can be checked if every path goes to a 0, then it is unsatisfiable. Okay, so I just now made a claim why that Boolean satisfiability is yes, Dhruv Patil, what's your question?
Sir, am I audible?
Yeah, you are.
Am I audible?
Yes, you are. Please go ahead.
Sir, could you please re-explain the notation? Because I
Yeah.
haven't understood it. The X or Y example, where is the if,
Where is the? Sorry, you broke up. Can you repeat?
which is the L?
Where is the end? Is it?
The
Is that your
notation, which one
question?
is if? Where is the if part? Where is the then part? And where is the else part?
The first one. No. If X is true, then there is a colon. Then part is to the left of the colon after the question mark. The else part is to the right of the colon. Okay. So this should be read as if X is true.
Yes, sir. So one is the.
Yeah, that's the one is always true, correct? So if X is true, then this says it has to be true. Okay, so and that's what this thing expresses. Okay, if X is false,
Yes,
then
understood.
it depends on what the value of Y is. Okay, if Y is all, then if X is false, then Y has to be true for X or Y to be true, correct? So that's what this thing is saying. If neither is true, then you know that it is false. Okay, that's how you can do. So it's really, you could, yeah. I mean, it's like if you made a truth table. A truth table is another representation of Boolean functions. Okay. Now, if you make a truth table, you can, check Boolean satisfiability. Given any formula, you can make a truth table for it. Okay. This this is a more efficient representation of a truth table. A truth table, whether you need it or not, you enumerate all possible assignments to all the variables in the formula. Therefore, you end up, the size of the truth table will be 2 to the n, okay, exponential. Whereas here, for some functions, the representation as BDD, if you use this if then else form, can be very compact. Okay. Yeah. So whereas a truth table representation for every function, it is exponential in the size of the variables. Therefore, that's why constructing a truth table to decide a formula is a very bad idea. Now, here I'm saying, okay, once you construct the BDD, it is easy for you to check. I mean, just like it is the case for the thing. So, but where is the catch? Why is it NP hard, Boolean satisfiability? I mean, that's because although BDD, as I just now claimed, is a fairly efficient representation in a lot of cases for a lot of Boolean functions, but there are some Boolean functions for which, no matter what variable ordering you choose, you choose. That is, no matter what order in which you choose to query these variables, the minimum size will be exponential, and that's why BDD is a good representation in a lot of cases, much better than a truth table representation. But it is not. It's still the worst case. There can be a size blow up here. But once if the Boolean function is such that you can construct a BDD, a compact BDD, then checking it would be quite efficient. Okay. Yeah, that's what I wanted to make. Okay. Now, let me go back to, yeah. What's your question? Yeah,
So,
Dhruv,
what are the advantages over other normal forms?
what are the advantage of BDD over other normal forms?
Yes, sir.
Yeah.
Can't the BDD
Yeah, you broke.
anyway replicated?
BDD, can it not be replicated? By that, what do you mean by that? Hmm?
Oh, anything which can be written in BDD normal form,
Yeah.
those formulas can also be written in the other normal forms as well, right?
That is right, but you cannot. The way you can check is satisfiability will be different. Like, for example, you can see this. Okay, there, this slide will kind of answer your questions. Okay, question. See, if you express in DNF, satisfiability checking is very efficient. Why? Okay. For example, this is a DNF form. Okay. Anything that is in DNF, it is satisfiable since it's a disjunction of cubes. Okay. It's a disjunction of cubes. So a formula in DNF form is satisfiable if at least one of its cubes is cube term is satisfiable. Okay. Now, a cube term, since it's a conjunction of literal, is satisfiable only if all the literals in it are satisfiable. Therefore, you can see you can just make one pass over the formula in DNF form, checking if any of the if you until you find one a cube term which is satisfiable, okay, which can, if you can make it have an assignment to make it satisfiable, and then you can, okay. The only way a DNF form can be unsat is if there is every cube term in the formula has a variable both in positive and negative form, then it is unsat, you see. So some sat, I mean, sat and unsat are very easy to check if you have it in DNF form, okay? But validity, checking is exponent. I mean, worst case exponential, okay? Whereas, it's the kind of the dual is true when you have it in CNF form. In CNF form, validity is quite easy to check, okay? Because it's a conjunction of these clauses. Whenever you have a conjunction of clauses, it is valid for all. If for every clause has to be satisfied. I mean, has to be true. I mean, for all possible assignments, okay? And a clause is false only if if that is the case. I mean, you can only have it such if it is valid only if it has a tautology as part of it, okay? Whereas satisfiability is hard. So you see, the structure of the thing makes it determines. Now BDD is kind of unique in that once you construct the BDD, maybe it answers Dhruv's question partly. Why is it? See, but converting, you could say, oh, I mean, I think Dhruv's question was partly, oh, why not? I will convert my CNF into DNF, okay? And then I will check, since SAT and unsat is easy for DNF, if I'm given a formula in CNF, then I will convert it into DNF and I can check this. I can check satisfiability. Aha, but there is a catch there, okay? When you convert a CNF into a CNF into DNF or vice versa, that itself, the conversion process itself can have an exponential blow up, okay? Therefore, see, look at the way that Boolean satisfiability is defined. No matter what form, okay, it is in, the idea is to check all of these three decision problems, okay? That's how it is defined. Therefore, you can't get away with this worst case exponential blow up. I mean, if it creeps in the conversion process. In BDD, which was Dhruv's question, where it creeps in is when you try to construct a BDD. Like I said, for a lot of functions, Boolean functions, there is very compact BDD representation, even linear in some cases. For a lot of cases, linear in the size of the variables. But there is always some function for which even to construct the BDD, the size, you require an exponential size, okay? And therefore, if you take into account that inputting, because complexity is measured, that even includes the input thing, so it blows up, okay? So that is the catch, and I hope that explains the thing. So they've already explained why that is the case, okay? So you cannot say, oh, I will choose that normal form in which something is efficient, okay? So this exponential blow up will creep in one way or the other, okay? Yeah, SAT solvers, unlike BDD and SAT solvers, they are the two most popular, practically widespread methods to check Boolean satisfiability, okay? Until SAT solvers in the 2001, after a few breakthroughs in the decade after the first decade of the 2000s, made SAT solvers so, after those breakthroughs, SAT solvers, became quite efficient in practice. Until then, BDDs were the dominant methods used for checking Boolean satisfiability. But nowadays, it is SAT solvers. Okay, but there are still certain applications for which BDDs are good. But SAT solvers, mostly all of them use, represent the formulas in CNF. Okay, there are some solvers called Horn-Clause solvers which use a slightly different notation. I mean, that's also CNF, but nonetheless, let me now get so there is this question. Then I just now said, oh, what if a formula is not in CNF? So SAT solvers expect you to input your formulas to check satisfiability always in CNF. What if your formula to begin with is not in CNF, but it is then you have to convert it. So won't the conversion process itself blow up? Yes, it does. Okay. For that, there is some kind of an encoding, which, by the way, if you have a propositional formula representing a Boolean function in non-CNF, that is not in CNF form, where does the blow up comes? When I say blow up, given a formula, I'm counting the blow up in the number of clauses that you need in the CNF form. Okay, remember that CNF is in negation normal form, where the negation appears only at the leaves. So if you have a formula where negation is not necessarily at the leaves, but at some other level, and you have all kinds of Boolean functions like exclusive or Boolean implications, equivalence, etc., then you see every time that you, in order to convert into CNF, you need to push the negation all the way to the leaves, and for that you have to use De Morgan formula. Okay, every time you push the negation one level, the number of clauses that you need will increase by 2. Okay, you can work it out yourself. So there will be an explosion. It will be an exponential blow up in the number of clauses. Now, I'm not going to get into this today. In the slides, I have all the details of sites and encoding. I may, if interested people can go through it. This is an encoding, wherein an arbitrary Boolean formula that is not in CNF can be converted into CNF without the exponential blow up, but by introducing additional variables that are linear in the size of the connectives involved in here. Okay, so almost all SAT solvers use this Citon encoding due to a logician called Citon. Use that. Okay, I'll let you study these slides so that I can move on to the thing. I've already given you one kind of an intuition as to why it is NP hard, okay, that the exponential blow up that you get in the conversion of from one normal form to another. The other thing is implemented. You see, look at this formula phi 2a, okay? When can it be, see, in order to check if it is unsat, okay? So see, this formula phi 2a has every literal both in positive as well as negative form. See, there's another easy case, by the way. If your formula is in CNF, and if every variable appears with only one polarity, okay, then the formula has to be satisfiable. Think about it, because the only way you can get contradictions and that can make the formula unsatisfiable is if a literal appears with the different polarity in two different clauses. So here, look at in phi 2a, look at the first two clauses, B and B. B appears in differing polarity. Now, if you look at second and third, A appears in different polarity. Third and fourth, C appears in different polarity. Okay. Now, in order to, because you have to satisfy all of them simultaneously. So if they occur in different polarities, you can only choose one possible assignment for B. You can choose only one possible assignment. It has to be such that it doesn't contradict the truth value of another clause. Okay. Sometimes what happens is this will require you end up checking, for some formulas in CNF, you end up checking all possible subsets or all possible valuations for the variables. And you can, that's why the real source is that there is some circularity argument in when the formula, the clauses have every literal or in both positive and negative form, or one or more literals, then you may end up having to enumerate or look at all possible subsets of clauses, which is exponential in the size of the formula. Okay. So this is kind of I'm relating this is because this is a motivation. So if you can eliminate in the formula such these kinds of conflicts, since there's a size of the formula, the number of literals in a formula is finite, and if you could look at only those variables that appear both as positive and negative literal, and if you could somehow eliminate them to produce some other formulas that have to be satisfiable in order to guarantee this the original formula is satisfiable, then if that guarantees you're removing this contradiction, maybe you can decide it. Okay, that is the was the motivation for this inference rule-based procedure. This is one of the earliest decision procedures that was proposed and constructed, that was based on this a principle called resolution. Okay, I guess some of you who have taken the logic course have seen resolution. Have you not? Can someone say yes or no?
Yeah, we have.
Okay. So, but there are 10 people here. So I guess there are some people here who have not taken, at least there were a couple of people. So let me quickly go through that. Okay. What resolution inference rule is. See, one way or the other, even present day SAT solvers, they all are based on resolution inference rule. But the way that the resolution inference is used and the heuristics that are used that are built on top of those things are what make present day SAT solvers so efficient. Okay, so it is very important for you to understand, in order to understand SMT solvers, SAT solvers, what resolution inference rule is. An inference, resolution inference, given two clauses C1 and C2, two non-empty clauses, with some variable C belong to C1. Okay, these two have at least one variable that occurs with both polarities. C belongs to C1 and say not C also belongs to C2, and both are the size of the clauses are greater than 1, then a resolvent of C1 and C2 on C is defined as follows. Okay, so you see there is a C in C1. If you have two clauses C1 and C2 where a particular variable occurs in different polarity, then you can resolve them. Okay, you could you could remove those C and C naught and then take a union of all the rest of the literals that appear in both in C1 as well as C2. Okay, that is, you take away C, C naught, and then you come, and the resolvent is the union of the rest of the literals in C1 and C2. Okay. This is, you can, what it says is resolution inference principle. It says you can always replace these two clauses by this clause, okay, because this clause is inferred by that, okay, that the resolvent is, I mean, the original conjunction of the two clauses is satisfiable if and only if the resolvent is satisfiable, okay? So that you see, so through this resolution, what you have done is eliminated one source of potential conflict, okay? Because this has one, the resolvent will have, it's also a clause, but it'll have one fewer thing. And it guarantees that the resolvent is what is so-called equisatisfiable, okay? If the original thing is satisfiable, if and only if the thing, okay? Of course, there is two other cases of things. So if you have a unitary clause, okay, both the clauses in your form in the CNF is unitary, and if they're contradicting, if A and A not, then you derive false, okay? That is a contradiction, okay, because this can never be true. But if you have, something else like this, obviously it is true, because if you resolve on B using the variable B, what you get is A or not A, which is always true. So this will always reduce to true, okay? The main, theorem of resolution principle is, as I already stated, C1 and C2 is equisatisfiable to R, which means that the original formula is satisfiable, conjunction of the two clauses is satisfiable, if and only if R is satisfiable. So that way, the idea is to keep applying the resolution repeatedly until you eliminate all the conflicting clauses. If in the process you end up getting a contradiction, then the original set of formula obviously is not satisfiable due to this theorem. If it is, if you have exhausted all possible way of generate all possible resolvents, because there can only be finitely many resolvents, because there are only finitely many literals in any given formula, then you can declare that it is satisfied. That's exactly what the Davis-Putnam strategy is, okay? Which was based on resolution principle. Given a CNF formula, okay, phi, you repeatedly apply resolution until you derive a contradiction or no new implied clauses, okay, no new resolvents. Sometimes the resolvents are called implied clauses because they are implied by the conjunction of the original two clauses are generated. You see, because they're all implied, okay, clauses, the resolvent is equisat with the original one. It is sound to add, you can add the resolvent to the original set of clauses without changing the satisfiability of the original formula. And that's what Davis-Putnam does, for procedure does, okay? So you keep doing this until, it has to end up in one of these two possible outcomes, okay? If phi is unset, if contradiction, else it is set, okay? So let me give you, for a moment, ignore the unsat course. I will show you a way of applying resolution. Okay, so I will concentrate on the second formula, phi 2. Can anyone tell me if phi2 is satisfiable or not, quickly. Yes, Dhruv?
Sir, it is not satisfiable because it requires. Oh,
Yeah.
wait, sorry, 1 minute. I misread it. I need to.
You see, I mean, this is a case where, some cases, depending upon what choice, you do, it is that your answer was
Sir,
correct. Okay. I mean, your first answer, although you wavered, is indeed
yes,
correct. Okay. So
yes.
let me take this example and show you what is, show you a resolution graph. Okay. Okay, how you could get indeed the result that it is not satisfiable, because you see, you can here, each step here is one resolution, and the variable that is used, it's usually called the pivot variable, the variable that appears in with different polarity that you use to produce the resolvent using the resolution inference rule, that is shown in that valley, okay, as B here. So I'm resolving the clause 1 and 2 on the variable, on the pivot variable B. So when you resolve on that, what you get, the resolvent is A, because A union A, that is A or A is A. Similarly, when you resolve here on C, this the third and the fourth formula, you get not A, okay? So then you repeat it, then you apply A not A, you resolve. Okay, the idea, the Davis-Putnam procedure, it says, oh, you have to add the resolvents to the original set of clauses, then keep, you have to also look at all the resolution on all the, between the, not only between the old clauses, but also between the old clauses and the new resolvents that are generated, as well as between the between all new resolvents. Okay, so you see, so you got a contradiction, and therefore, in three resolution steps, you were able to decide that this one was unsatisfiable. Okay, so but it's not always the case. There's no unique um solution, unique proof. This is called a resolution graph, or it is actually also called a resolution proof, because that's a proof of unsatisfiability of the formula phi2 using a resolution principle, because every step here is consists of an application of a resolution inference, and that, as I described, is a sound inference rule. So so if you derive a contradiction, now look at here. Here I have the order and the choice of your the clauses that you use, and the variable that you use to pivot very much depends on how big your resolution graph or the resolution proof is. Here I've chosen a different set of clauses in different order and pivot variables, and you can see the depth of the tree here. I took longer and more number of resolution steps to get the contradiction. Okay, and therefore, so while Davis-Putnam's procedure is indeed decision procedure, which means that it always terminates, and when it terminates, it comes up with yes or no answer. Either it is unsat or it is sat. Okay, but sometimes it can be efficient, depending upon what order that that you choose the thing in. Okay, so let me see. Okay, so now I'll take one more example.
Sir,
Yeah.
sir,
Yeah.
can you explain the second graph?
Okay.
The second one, like not this one, the second one.
Yes, yes. Let me get that. I think it's this one. No, not this one. I don't know where it went away. Yeah. So
This
here,
one.
instead of resolving over B like I did there, I chose to use the clauses 1 and 3 to resolve over A. Okay. Using A. So I get B or C. Yeah.
Yes, sir.
And then what do I do? I use B or C to resolve using A, or I mean using the original. I mean, this is a resolution on the first resolvent you got and the original clause. Okay.
Hmm.
See, this is important in when you're doing using Davis-Putnam procedure. You have to exhaust all possible until there is even one pair of clauses, whether they're old or new generated clauses. Okay, you have to consider all possible, unless you get a contradiction prematurely. Once you get a contradiction, you can stop. Otherwise, you have to keep going. Okay,
Hmm.
until you're sure that no more new resolvents are produced. Okay, and that's what here you had the misfortune of choosing a difference. So then that's how it keeps going. Okay, I chose between
Sir,
this
can
and
you explain the third one, like A or C? What did you do with that?
what do I do with this? This produced A or
A
C.
or
Yeah.
what like
Yeah, with A or C, then I used the third clause and the newly generated resolvent to pivot over A to produce C. See?
and then you again used it with the fourth one.
Yeah, then I again used it. Oh, no, no, no. Then I use the same resolved A or C with the fourth one to get C naught. Okay. Eventually, Davis-Putnam procedure will have to, the only way it will produce a contradiction is through resolving unit clauses that are contradicting with each other. Okay. So you see, every step reduces one source of conflict, and that's how you have to do. The if you choose the clauses and the pivot variables such that you can get unit clauses that are contradicting as fast as you can, Davis-Putnam procedure works very well. Okay, but how do you know? You don't know in advance. Okay, so there could be lots of different strategies that you can add and you can use to decide that order and so on. Okay, but that's how it is. Okay, eventually you can get a contradiction only by reducing them and producing some uh, possible unit clauses that are conflicting with each other. Yeah. Okay.
Thank you, sir.
Yeah. Okay. Yeah, I'm going to just for your thing choose the not the first one. Yeah, 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 yeah. This one. Okay. So the first phi one here, I've used plus to represent disjunction, dot to represent conjunction. Okay. So I've chosen the first two resolution to do. Okay. I can do choose 1 and 2 with C as the pivot variable that produces A plus B plus naught F. And similarly, I can choose 2 and 3 to resolve over B to produce this. Okay. And you can see, okay, in the interest of time, I'm going to not ask you, I'll show the proof. And you'll see this is a case where you will end up satisfying. Okay. After that, you can once again do, there is a possibility to do resolution between 1 and 2, 3, which produces 1 and 2, 3 on C, which produces this resolvent. Similarly, you can choose 1, 2, and 3 to produce this. And after that, you can choose 1 dash 2, 3, and 3 to produce this. After this, no two pair of clauses produce any new resolvents. Okay, still resolvable, but they end up producing something that already exists. So this is kind of the closure. Okay, you produce all possible resolvents without, so no more new resolvents is able. I mean, you can add, and therefore this is a situation where the original formula is satisfied. Okay, that's how Davis-Putnam's procedure works. Okay. Any questions? There's this notion of unsat core, okay? Unsat core, if a formula is unsatisfiable, phi 2 is unsatisfiable, so are phi 1a and phi 1b, okay? When something is unsat, there's always some subset of the original set of clauses which are contradictory with each other, but no smaller subset of a smaller subset is satisfiable. Okay, I mean it can be contradictory. Now, in phi 2, you needed all the 4 clauses. Okay, the proper subset of the original set of clauses which are sufficient to show a contradiction is what is called an unsat core. Okay, and there can be several unsat cores because there can be several different subsets which are contradicting with each other that results in the original formula being unsatisfied. And the smallest of them, such subset, is called the minimum unsat core. Okay, and that is quite useful when you want to, in verification, this identification of unsat core is quite useful to do a lot of interesting things. And SAT solvers, besides like Z3, besides giving you results SAT, unsat, valid, okay, and in the case of SAT, giving the model, it also is able to, if it is unsat, you can ask for it to give it an unsat core. Okay, sometimes it may give minimum, but it certainly gives an unsat core. I leave it as an exercise for you to, in the case of phi 2u, the smallest unsat core, requires all the 4 clauses in the original formula. In phi 1a and 1b, a subset will suffice. Okay, because they're also unsat. And leave it as an exercise for you to find out what that subset is. Okay, but you can compute that automatically as well, but that's an expensive procedure. But nonetheless, you can do that. Okay, the drawback of Davis-Putnam procedure is that it is memory intensive. That's why a Davis-Putnam strategy after resolution principle was invented in 1960, and Davis-Putnam strategy was probably late 60s, 70s, but it was never scaled beyond formulas which had a few tens of variables or maybe 100 variables and a few tens of clauses. Okay, the reason was it is memory intensive. Okay, that you needed to keep not only all the new resolvents, new clauses that is produced as a result of resolution, but also the original set of clauses, and therefore soon, okay, only then you can your procedure can terminate, and therefore it was it was not scaling beyond 100. And of course, the other two things, it is the order of variables to use in resolution, as well as the choice of clauses that you use had a significant impact on your thing. And then how exactly you do that, it was not very goal oriented, and there was too many non-determinism in the choices that it had. Okay, so the next thing was this. I use the term DPLL, and the expansion for this is Davis, Putnam, Longman, and Loveland. Okay, and this strategy is due to those people. Here, the idea is to always use, instead of using resolution on any non-unitary thing, the idea is you always given a formula, you always, one of the clauses on which you choose to resolve, okay, is you choose it as a unit clause. The other clause can be non-unitary, okay? But one of the clauses is, in such a resolution is called unit resolution, okay? It says that you always choose, okay? When you do this, you can have only two choices. If one of the clauses is unit, then the resolvent will automatically, P and not P, you will get the union of this thing. If it is, if P and P you have, then the other rule will reduce it immediately to true, because if one of them is unit, then the only way you can satisfy them is making P to be true. And once P is true, the other clause will, simplify to true, okay? In this case, you can get rid of those, those two clauses. And that's what here BCP does, okay? Given any formula, if the formula has one or more unit clauses, it applies this unit resolution, which is effectively plugging the assignment to make that unit literal to be true into the rest of the clauses, okay? To simplify all the clauses. So some of the clauses may reduce to might simplify, and some of them may reduce to true, in which case they'll disappear, okay? And that you do that repeatedly until you cannot apply any more unit resolution, okay? That is fairly efficient, okay, to do. And you see, if this is the case, then the original set of clauses either reduces or will reduce away to true, or in some cases false. If it reduces to false, you're done. Okay, you're done. And that's what this thing does. Okay, so what you start is, this is DPLL. Okay, so given a formula in CNF form, you apply this Boolean constraint propagation. That's what BCP stands for. This is an iterative thing until you keep applying these rules until what can happen? Until you one of the clauses will simplify to false, in which case you know that the original clause is unsatisfiable, so you say false. Okay, if it is simplifies to true, of course you have other clauses still. If all of them simplify to true, of course it is true. If neither of these is the case, then what it means is there was some subset of the clauses which did not simplify to true. They did get simplified in terms of some literals being thrown away. So, but now there are no more unit. Probably there are no more unit things. Then what do? What DPLL says is you choose arbitrarily some variable, okay, in that appears in any one of the remaining clauses in the formula, and then you make it, you can then you recurse it, force it to be true, and then you repeat this BCP recursively. Or you also make it to be false and then repeat the DPLL. Okay, so that's how we keep propagating. Okay, and this is one way DPLL, and present day stats always use DPLL procedure to do it. The main drawbacks of DPLL is, every time there's no learning in this thing. Okay, here I'm not learning means I don't use it in the sense of machine learning, but here it is something that you can actually learn when you get a conflict. So maybe I'll show one example. I'm going to go today till 6:15 because I want to complete just the basic version of DPLL. In the next class, I will add all the improvements, breakthrough improvements over DPLL that contributed to what present-day SAT solvers are. So bear with me till 6:15. Okay, so let me first show you if this DPLL in action. No. No. Oh, it is here. Okay, let's suppose that you have 6 clauses in your original formula as shown in the left side, on the left side, the blue shaded thing. So here is DPLL, okay? So now there's no unit clause, okay? So BCP is nothing to, you can't apply any unit resolution. There's no BCP to be done. Therefore, you have to make a choice. You have to choose a variable and assign it some either true or false. Here, a solid edge means that I chose x1 and chose it to make it true. Once I make it true, what will happen? Unit resolution has when I do BCP, the BCP is, although I stated it as unit resolution, you can think of it as plugging in 1 for x1 in all the clauses. If you did it, C1 reduces to x2 and not x4. There's no C2 reduces to not x2 and x3. There's the rest of the things don't have any, do not have x1. So you still, C1, C2 got simplified, but you still don't have all the clauses are non-unit, okay? Non-unit, and therefore you have to make another forced choice, okay? So suppose I choose x8, okay? The choice that you make is left up to you. You can choose it arbitrarily, okay? So you choose x8, and I choose it to make it 1. Once I make it 1, there will be further simplification. Okay, you can see some of the clauses that have x8. All of them have. There's only one here, which is C6, which becomes 1 becomes 0, and therefore that gets simplified. but still that's the end of this. Now you have to make another choice, okay, with X7. After that, when you do BCP, there is a whole bunch of recursive BCP happens. The moment you get X7 become 0, I'm making a choice to be 0 because the dotted lines gives a 0. 0 makes this become unit. C5 becomes unit. So once it becomes unit, BCP has to make X5 to be false because that's the only way you can make C5 to be true. And when you make X5 literal to be true, then this, as you can see, when I plug in X5, where else X5? I mean, X5 appears yeah, X7 forces C6 becomes unit. It forces, because X7 has already been, X7 is 0, this term is already gone, so it forces C6 to be unit, which forces X6, not of X6 to be 1. Once you make that choice, I mean, also C5 is 1. I mean, C5 is unit. So two of those decisions will force the decision on X5 and X6 to be 0, and then you see X4 becomes C4 becomes unit, which forces X4 to be 1. That's what happens here. And similarly, X2 and not X3, and then which will result in C3 getting simplified to false. Okay. So what that means is then that is a situation where there is a conflict. What this means is this choice of X1, the explicit choice that you made to make X1 to be true, X8 to be true, and X1, X7 to be false is not a satisfying assignment. In such a case, what do? DPLL, what it says is, you have to backtrack, okay, and flip one of the choices in the partial assignment to the variables that you have made. Okay, so and that's what you will have to do. Okay, in this case, what happens is if you can, when I see, so this resulted in a conflict, like I showed before. Then you backtrack, okay, to the earliest level. Since you know that choosing X7 to be 0 is resulting in a conflict, you have to flip that decision, get X7 to be 1, and then do BCP again. Okay, and that if you did it, you can do it at your leisure. It'll make it'll still does not produce the BCP does not produce any new unit clauses. So you'll have to make you have to make an explicit voluntary decision. And I chose X5 to make it 0. And then you get, that, also makes, okay, still does not produce. Then when you choose X4 to be 0, it produces the same conflict in C2, okay? In C2. Earlier also C2 was the result of the conflict. Similarly, if you now flip, backtrack to X6 and then make other decisions, you will hit the same conflict in C2 again. Okay, so this is kind of this is the drawback of DPLL. Why DPLL? Because of the unit resolution using, you have, the BCP is quite efficient, but you need to backtrack, okay? And in the case where you hit the same conflict, that is one of the drawbacks of DPLL, okay? But while BCP is hard, it is very sensitive to the decision of the variables that you choose to make voluntary assignments, and that can end up hitting resulting in the same conflicts where the source of the conflict is the same. So here, the reason that you're hitting the same conflict is because once you make a voluntary decision on X1 in this case, it so happens that the original set of clauses is such that X1 implies the X4 to be 1, okay? That is, X1 has to be, X1 and X4 have to be, cannot be, both cannot be 1, okay? I mean, I'm sorry, both, once you make X1, X4 cannot be 1, okay? But here, due to my involuntary decisions, I was making X4 to be 1. Now, wouldn't it be good if I somehow learned that from the conflict, okay? If from the first time I get the conflict, if as a result of making X1, if somehow, see, in this case, when I made X1, when I came to the third level decision, when I made X7 to be 0, that kind of forced X4 to be to become 1, which is not possible, okay? And the fact that you can learn from this conflict is, if I made a choice of X1 to be 1, if I can learn that X4 can never be 1, because that is, given the original set of clauses, then maybe you can prevent this the same conflict by occurring again and again repeatedly. That was the first, a breakthrough that was, that was done. No learning. It does not. Any learning throws away all the work performed to conclude that the current partial assignment is bad. By bad, I mean it results in a conflict, and revisits bad partial assignments to the same, to a conflict due to the same root cause. In this case, it was the root cause was because X1 and X4 could not be 1 simultaneously. The other thing is, why backtrack always to the earliest, to the latest level? Could you not jump levels to do it, okay? And the third thing was, can you have some very good heuristics to make your decisions? Because as I told you, the way that you make voluntary decisions, the way you choose the variables, which variable you choose to make a voluntary decision on, and whether you choose to make that 1 or 0 very much impacts the depth to which you need to go before you can declare the original formula to be sat or unsat. This is very much similar to which pivot variable that you use using resolution. Okay, here what you're using. These are the 3 significant breakthroughs that happened in 2001 to 2010 that gave several orders of magnitude of performance boost to DPLL algorithm, enhanced DPLL algorithm, and that's what these 3 ideas is what we will look at in the next class. Okay, yeah. Any questions? Okay, yeah. I'm going a little bit deeper into this thing in the next couple of classes, although you may not need as much of knowledge about SAT, although you could say that you need in order to understand some of the decision procedures that we later come up with for DNN verification. In order to understand those things much deeper, as you can see, some of you who went to today's tutorial there, that was probably a high-level tutorial that you did. You must have, I hope you got some useful information there. But in this class, you will, my goal is to go a little bit deeper into the things so that you will understand the tools that are built for DNN verification in a much more deeply, so that you will appreciate what the strengths and weaknesses of those tools are better. Okay, that's why I'm spending maybe 2 to 3 two more classes in addition to this one, 2 to maybe 3, depending upon the pace I go on, looking a little bit under the hood, is the way I put it, of SAT and SMT solvers, so that you will understand the later tools for DNN better. Okay, so yeah, but we will get to DNN verification tools and more abstraction techniques, etc., that are used to scale up pretty soon. Okay, I'd appreciate your patience. Okay, any questions? Okay, thank you. I will upload this lecture video and the slides promptly today itself, so you can review it. Okay, I'm going to, if there are no more questions, I will end the session now.